So here are some of the classic circular motion problems. This first one, the rectangle just represents kind of the tabletop, and so this is just a string with a mass on the end of it. The string has a length L, the mass has a mass M, and all we're going to do is kind of whip it around in a circle horizontally. So this is like the string, and we're going to grab it from this end, and we're going to whip it around in a circle, and then we can ask some questions. And so all of these are just F equals ma problems. The force, now could be lots of forces on this object, and if you drew the force on this object, if you look at the vertical direction, well, there of course is weight, and this is the tabletop, and then back towards the center is the tension, meaning the strain. These two forces are balanced and really don't have anything to do with circular motion. The only thing causing circular motion is the tension in the string, and then what we can do is replace this by v squared over r. Again, centripetal acceleration, one of the things that we will use a lot, can be replaced by v squared over r, or can be replaced by omega squared r. Oops. What I said, omega squared r. And what that means is we know that v equals omega r, and you can make a quick substitution to find those values. Again, this is tangential velocity, linear velocity, velocity. Any of those words mean the same thing, just normal velocity. Again, this is in meters per second. And then omega, which looks like a W, but it's an omega, is in radians per second. Okay, and this just says this is kind of your spin rate. This is how fast you're moving, and those things are related by how far you're away on this. So if we look at our typical circle, if this is some spinning disk, the further you move away from the center, meaning r, you increase r, based on a constant rotation, the faster you're going to be moving. Well, of course, or you're going to be going a bigger distance in the same amount of time. Okay, getting back to this one. So the problem that you might run into is that they might give you some string that has some breaking tension. Okay, so let's just say this particular example, we know that T max is, let's say, 100 newtons. And the length of our string is 2 meters, and we're trying to spin a 4 kilogram mass. And the question is, well, how fast can we spin it? Well, the maximum that the tension can be, meaning the maximum force that can cause circular motion, is 100. Our mass is going to be 4. What's v squared if we're spinning around with a length of string of 2? So this is just 2, and this is 50. And so v ends up being the square root of 50, which is like, well, 7.1 meters per second or something. Okay. The next one is just basically a car. And remember, how do you turn? How does your car turn? Well, if you've ever experienced going in winter and you're going this way, you're going this way, and then going this way, and you try to turn on ice, well, your car might actually turn a little bit, but you're going to skid that direction rather than actually turn because there's no friction. Friction is the force that allows you to turn in a car. And so when you're thinking of doing one of these problems, it starts out with F equals ma. Mu mg is the force that allows you to move in a circle, and then you do something like this. And again, you can see that the mass cancels, and so you can figure out how fast you can go. So we're looking for v would be mu gr. This would be the maximum you can go based on the road conditions. And so if it's snowing, or it's sleeting, or it's slippery, then mu is going to change. And as mu gets smaller, so does the velocity that you can go safely. And when I say safely, I mean without slipping or without skidding. And again, if you drew a free body diagram for your car, and this would be kind of at this moment right there when you start to turn, friction would be inward. Again, the force of circular motion, the force causing circular motion. There is no force of circular motion, just like there's no force of motion. There are applied forces, there are forces that cause changes in motion, but the force that causes circular motion here is the force of friction. So just set that equal to ma and replace a by v squared over r, and you get a relationship that makes sense. If you take a bigger turn, so this versus turning around and taking this long, well, then you can go faster here because you have a bigger radius. right? This is our roller coaster or fighter jet, anything where we're looking at a vertical loop. And we're going to look at the top and the bottom separately. So we have a mass that's going to slide down this roller coaster. We're going to go whip around this thing. Realistically, at the top, what you have here is you have gravity pointing down, but you also have the track pushing you down. And if you go really fast around this track, the track itself actually has to push down as well, because what we're going to say here is the N plus mg equals mv squared over r. Both the track and gravity together work in combination to provide the force that causes circular motion. On the bottom, meaning when you're coming out of your the loop-de-loop, you got the normal forces up and mg is down. In this case, N minus mg equals mv squared over r. And again, at the top, gravity is helped by the normal force. At the bottom, the normal force is hurt by gravity. Gravity wants you to go down. The normal force has to be upward. The normal force is inward. The normal force is the thing actually causing circular motion, and it has to overcome gravity, and it's typically bigger than your weight. So if you've ridden a roller coaster before, you feel light at the top, meaning small normal force because gravity is helping out, and you feel heavier at the bottom because the normal force is bigger than mg, right? The normal force, if we looked at this bottom equation, the normal force would equal mv squared over r plus some mg, right? This factor in addition to mg. Okay, if we want to find the minimum velocity to order to make it around the loop, typically we're talking about the velocity necessary at the top. We're looking at the same thing, but if you're looking at the minimum velocity, well, the minimum velocity doesn't require any help from the roller coaster itself, and so we would just say mg equals mv squared over r. Again, I'm just going up to this equation saying, well, that's equal to 0 at the minimum, and so then you get v equals the square root of gr, which is a nice thing to remember, not something that you have to, but the minimum velocity at the top of a loop, it doesn't matter whether it's a roller coaster or you're taking a bucket and swinging a bucket around, or you're taking some ball, meaning what's the minimum velocity you can go around, because if you go slow enough, then you're going to get slack because it's going to be falling rather than actually moving in a circle. But if you want to actually take this thing and move it in a circle, the minimum velocity is the square root of gr, and in this case r equals the length of the string. In this case r is the radius of this circular loop. There's our classic tetherball, and one of the assumptions we make on tetherball that it's not changing the plane, it's just going out of the page and then into the page. It's just whipping around this thing. Vertically, you might be looking at it, something like that. And so what we're going to do here is we're going to do the same thing we always do. Draw a free body diagram. mg's down, and at tension is up the rope at some angle. That's it. Those are the only two forces on it. There's no force of circular motion. Now, there are forces in here that are causing circular motion, but those are the only two forces on the ball. mg down, and the rope is pulling up at an angle. So instead of x hat and y hat, what we're going to do is we're going to look at y hat and r hat representing the radial direction. We can't really say x hat because at this point it's going inward here, in, but it's always in r hat direction. Vertically, what we can say here, see how this is the angle, and that's a little tricky. At this top then, when you try to break down tension to its pieces, you're going to say that this is the r hat piece and this is the vertical piece. That's the angle. So the vertical piece is actually t cosine theta. Now that's not what we normally do, because normally the angle is with respect to the horizontal rather than the vertical. So hopefully you can imagine that sine and cosine would have switched. So t cosine theta is the vertical up force by the rope. The rope is pulling up, mg is pulling down, and we're not actually changing our value vertically, right? The tether ball is just whipping around the post, so we know that's equal to 0. In the radial direction, we have t sine theta. The string's horizontal component is the only force causing circular motion. Circular motion then mv squared over r. One of the tricky parts is to represent what is r. Well, r is the radius of the motion. The radius of the motion is represented by this dotted line right here. This dotted line is a certain distance. Well, based on the length of the string and the angle, r is L sine theta. So L sine theta can replace r in that equation. And again, typically the problem is that you're looking at the visual of this going around. You know the mass, you know the length, and you know theta. Those are the three given pieces of information. If you look over here, if you know the mass and the angle, you can find the tension. If you know the tension from the top equation and the angle and the mass and the length of the string, L sine theta, then you can use this to find V. And then once you find the velocity, okay, so let's say we know the velocity and we know the tension. This solves us for the tension, this would find the velocity. Once we know the velocity though, we can find the spin rate, we can find the frequency, because we know that omega is just 2 pi f. Again, this is in radians per second, and this is in revolutions per second. And hopefully this equation makes sense. Radians per second, and revolutions or rotations per second, or cycles per second. Each cycle, though, around is just 2 pi radians. So it makes sense that if you can do, let's say in a different example, if you can do a frequency of, let's say, 5 revolutions in a second, but if each revolution is just 2 pi radians, then it should make sense that then you can do 10 pi radians per second, right? This is how many angles you can cruise through every second, and this is how many revolutions you can do per second. So this relationship is pretty nice. We also know that the period is 1 over the frequency, right? If you can do 5. So when you look at this, what you're going to do is first realize that this direction here is the radial direction, and this force, or this direction, is kind of the vertical direction. So these are the two things we're going to break it down. Our car isn't having any acceleration in this direction, but the acceleration is inward, which is basically just left on my picture, which we'll call the radial direction. If you draw the free body diagram, that's not the hard part, because we know as gravity's down, we know the normal force is perpendicular to the surface, and if we're going to go really, really, really fast, then we would be looking like we might slide off, and so friction is going to help us and go down the ramp. If you were going around this really slow, like you were in your car, not an NASCAR car, and you were going slow enough, you might actually slide down, and then friction would go up. But realistically, we're going really fast. So again, this whole scenario was looking for like the maximum velocity you could go around this particular banked curve, and so then friction would go down the ramp. The hardest part is, you see, if this is our coordinate system and this is up and down, we need to break the normal force and the force of friction into its pieces. Hopefully you can see that the normal force has this piece going in and that piece going up. And the force of friction has this piece going in and this piece going down. We just need to sort that out. This makes this free body diagram way messy. Again, draw that again. It's nice and easy when you look at it in this way. And if you try to put on all the components, it can get messy. The force of friction is both left, meaning inward and down. The normal force is inward and up. And what we know for the y-hat direction, well, there's no acceleration in that direction. When you go around this banked curve, we're not going up or down the bank at all. We're staying at the same position on the bank. So we come in, we're going around that. But we know we have to change direction because we're moving in a circle. So there must be some radial force. Okay? So I'm just going to draw the normal force first. So let's take a look at that. And so just one dot and then the normal force. Okay? So that arrow represents the normal force, and I want to break it down into its pieces. I have the inward piece and the upward piece. This angle is theta, but then this angle is theta. But if this is theta, that's some other angle we could call alpha, which makes the top angle up here, this angle is also theta. That's theta, that's the normal force. And so here we have the normal force cosine, and here the normal force times sine. So we understand what those pieces are now. Okay, so n cosine theta is up. Okay, and sine theta is inward. Okay, and now we've broken down the normal force. Do the same thing for the force of friction. The force of friction we know is down the ramp, which means it's inward and down. This is theta, this is theta. So the down part of the force of friction is the opposite side, so it's sine theta. So minus the force of friction, sine theta, of course, minus mg, and that equals 0. And again, don't overcomplicate physics. This is just the up minus the downs. And it's equal to 0 because we know we're not accelerating in this direction. Vertically, we're not doing anything. Radially, we're accelerating inward. Again, this was the force of friction. This piece of the friction is the adjacent piece, so it's the cosine. So plus ff cosine theta equals mv squared over r. Again, both the normal force and the force of friction are both pointed inward. Look at this picture again. This is the cleanest picture. The normal force has an inward piece and the force of friction has an inward piece. Both of those pieces cause the circular motion. The normal force has a vertical component that's up, meaning positive. Friction has a down piece, right? It's left and down, and then gravity, of course, is down, and so both of those are negative. This is equal to 0 because we know we're not accelerating in this direction, and those two forces are the ones causing circular motion, and we've replaced centripetal acceleration by v squared over r. You have to remind yourself that the force of friction is equal to mu times the normal force, so you can put mu times the normal force into this top equation, and so n cosine theta minus mu n sine theta minus mg is equal to 0. So you could use this to solve for the normal force. That just means that the normal force, if I factor that out, minus mu sine theta, and I move the mg to the other side. Again, I did two steps right there. I moved mg over here, and then I factored, and so then the normal force is equal to mg over cosine theta minus mu sine theta. And then I can take that and plug it in right here because I can rewrite this equation as n sine theta minus mu n cosine theta equals mv squared over r. And so then this value of the normal force can replace there and there, and we get some nasty algebra, which I'm going to run out to. And again, you can refer to other keys or other things to find out that full scale algebra. And again, this is for the maximum velocity. If we wanted the minimum velocity, the force of friction goes in the other direction, and hopefully it's not too hard to imagine that instead of inward and down, left and down, it'd be right and up. And so both of these signs actually switch values. And so then it's not really too hard of an adjustment because we just switch them down there as well. Okay, and so that's the banked curve. That's probably the hardest one, and again, you really have to think about breaking down the normal force and the force of friction into their two radial and vertical pieces.